Phosphorus is a pillar upon which human society is built. So we have built our society around the energy from fossil fuels, water for irrigating our crops, and predominantly nitrogen and phosphorus fertilizer to help those crops grow. And fossil fuels are replaceable by things like wind and solar and batteries. Nitrogen is gettable if you have energy, but phosphorus is finite and irreplaceable. And in that sense, it sort of sets the bound on how much life we can have.
Welcome. I'm Dale Walkinen, and this is Facing Future. Phosphorus is essential for all living things. Although it is a common element, only a finite percentage of it is actually available to us. It's the P in the widely used NPK fertilizer, and it is a component of lithium iron phosphate batteries used in EVs, for example. It's also in flame retardants, food additives, steel, concrete, and in your cookies. The concentration of high-grade phosphorus in a few countries, mostly in Morocco, raises questions about the future of food and geopolitical conflicts. As Isaac Asimov put it, life can multiply until all the phosphorus has gone, and then there is an inexorable halt, which nothing can prevent. While farming uses large amounts of phosphorus, it recycles very little of it. Nutrient becomes waste. Phosphorus-rich manure and fertilizers run off with rain and pollute waterways, resulting in toxic pea soup lakes and dead zones. The oceans in coastal areas can become anoxic, unable to sustain multicellular life. Phosphorus, which literally means light bearer for its phosphorescent quality, gives life, but in the wrong place and in the wrong quantity, it can spell disaster. With me today to discuss all of this and what we can do to keep the phosphorus genie in the bottle are Eric Roy, Associate Professor at the University of Vermont and Director of the Casella Center for Circular Economy and Sustainability, and Stephen Porter. Welcome back, Stephen, again. Acacia Professor of Ecology, Evolutionary and Organismal Biology, and the Environment and Society at Brown University. He's also the author of Elemental: How 5 Elements Changed Earth's Past and Will Shape Our Future. So welcome to you both.
Thanks, Dale. Nice to see you.
Yeah, thanks for
Hi,
having
good to So to begin, let's talk about what phosphorus is and where it comes from.
Yeah, maybe I'll start off with that. So all life on Earth, and as far as we know, all life anywhere, depends on a few critical atoms that it uses to build all of the building blocks of life. And phosphorus is one of those. In a previous episode, we talked about nitrogen, Dale, and that's another one. Phosphorus is one of those, but it's very different from all the others. And it's very different from all the others in part because it comes only from the mining of rock. So nitrogen, for example, can come from the air, and it's wildly abundant in the air. So we just need energy to get it. Carbon, another one of those elements, comes into plants via carbon dioxide and photosynthesis. But phosphorus comes from the rock. And so it presents a challenge to all organisms to extract it from the rock and get it into their cells. It is also a pillar upon which human society is built. So we have built our society around the energy from fossil fuels, water for irrigating our crops, and predominantly nitrogen and phosphorus fertilizer to help those crops grow. Those are really the pillars upon which we're built. And fossil fuels to provide energy are replaceable by things like wind and solar and batteries. Nitrogen is gettable if you have energy. But phosphorus is finite and irreplaceable. And in that sense, back to the Isaac Asimov quote, it sort of sets the bound on how much life we can have. It's our ability to get and recycle phosphorus that permits life to grow to the extent that it does on Earth. And it does set a hard limit in a way that energy and nitrogen do not, because they're gettable.
Yeah, I actually think Asimov also called phosphorus life's bottleneck. So ultimately constrains what's possible on a large scale. And my understanding, this is not my field, but even folks looking at exoplanets and like way out into space to understand whether or not planets or moons could host life, one of the things they think about is whether or not phosphorus is likely to be there.
Are there ways of seeing if there's phosphorus in other planets?
I think there are, and it's really wild that we can do that. And that's not something I do, but yeah, people think about that.
Well, phosphorus is also in our food, in
Mhm.
everything. It's in all living cells.
Yeah.
So we are blissfully unaware of it. And it's really kind of shocking and amazing that it only comes, well, it mainly comes from one place. Morocco has most of the world's reserves of phosphorus. So one wonders what's going to happen in the future as everyone wants to get more phosphorus to power their batteries and nourish their crops. How's that going to play out?
The phosphorus, there are phosphorus deposits outside Morocco. They do have the majority of it.
Mhm.
And this is really not a story, and I think will never be a story about EV batteries. This is really a story about farming. But the vast majority of phosphorus that humans use, that we mine from the earth and move around and dump on and put out there in the environment, that's a farming story. EV batteries are you're already seeing recycling at very high rates. And even if everybody in the world drove an EV, the amount of phosphorus that we would use for fertilizer would dwarf every single EV battery. So there's a connection in that there is phosphorus in lithium iron phosphate batteries, but the real story here is how we conserve phosphorus on our farm fields. As you put it in the introduction, put it where we want it and kind of keep it there. And that is a real challenge, and we'll get into that, I'm sure. And Eric is a real expert in this space. But I just want to make the distinction that I think EV batteries are not really the main story here.
Well, the farming uses of it are what's the problem in the waterways of the Gulf of Mexico, dead zones and so forth. We remember phosphates in detergents and that controversy to get them out of the environment and keep them where they belong. So what were we doing to make that happen?
Yeah, there's been a lot of effort, so much effort over the past several decades on phosphorus management. The issue with detergents, for example, in Lake Erie, an initial step was kind of removing phosphorus from detergents that yielded immediate benefits in terms of water quality in Lake Erie. And so there are sometimes issues like that where we can make quick progress. That's a good example, or maybe upgrading wastewater treatment that can yield some quicker results. But managing phosphorus on agricultural fields is more challenging. We referred to the type of pollution from agricultural fields and even urban environments as non-point source pollution. That means it's not just coming from a single pipe or location where we can slap on some sort of treatment system or we can remove something that will influence all of the water moving through the watershed. Instead, it's a bunch of tiny areas across the landscape where phosphorus is kind of bleeding out into waterways. And so to manage it better, the first step in my mind is to stop adding way more than we need when that is occurring. So to reduce the excess that we're putting out in the environment. Um, and you would think that there's financial incentive to do that because fertilizer costs money, but historically, it has not necessarily been the case that economics really translates into super efficient use. But as we kind of first draw down the excess, then we have to think about how can we recover what we do put out as efficiently as possible. So, we really want that phosphorus to end up in the food that we eat and not to be out in the environment, whether it's in soil or water. And then, there's also another step, which is how do we recycle phosphorus more in our systems? Because even if we're efficient, but it's still kind of a one-way street, all leading to water in the end, over a long period of time, that's not sustainable. So how can we learn how to recycle phosphorus better? And then, all right, we're going to do the best we can, but we're not going to be perfect. How can we kind of restore the landscape in ways to help resist the movement of phosphorus down into lakes and coastal waters where it causes the most problems? So kind of efficiency, recycling, and ultimately just trying to create more buffering to kind of prevent the phosphorus from moving downstream are the approaches we've been looking at.
just piggyback on that, Dale, for 1 second. So I think it might help the listeners of the show to back out and think about two sort of extreme end member systems. So you can think of the soil as a bank account. It has a certain amount of phosphorus in it. And in a forest ecosystem, pretty much anywhere in the world, there are very, very small inputs to that bank account. So you can think of it as a very small salary of phosphorus. But the losses, the expenses from that bank account are also very small. But what's happening a lot is that plants are taking money out of the soil bank, and then when their leaves fall, they decompose and go back into the soil bank. And the vast majority of phosphorus that any natural ecosystem uses in any given year to support growth is recycled.
Mhm.
In contrast, if you look at a modern farm, and even a not so modern farm, what we're doing is we're mining phosphorus somewhere. We're using acid to turn it into fertilizer. We're shipping that fertilizer to the farm. We're dumping a bunch of it on the farm field. In the best case scenario, like as Eric was mentioning, in the best case scenario, every atom of phosphorus that we drop on that farm field goes into a crop for us to eat. That's like ideal. That never happens, but that's ideal. But even in that ideal case, those crops get shipped off of the farm field, either into the mouths of animals or into the mouths of humans, and excreted very far away from where that farm field is. So instead of having a bank account with very little input, very little output, and lots of recycling, our agricultural system by default, because we are not going to the bathroom on the farm, and neither are our animals, by default, it's a flow through system with huge amounts coming in, very little internal recycling, and huge amounts going out. And even if we do everything right on farm management, right, and get most of that phosphorus into the mouths of people or animals, it's still a one-way street, right? I just want to make that contrast clear for the viewers because, like, yeah, there's a lot of stuff we can do on the farm, but even then we have this challenge.
Yeah. And sometimes you'll hear folks claim that we should move to systems without phosphorus inputs. And I would argue that that will ultimately fail over time because, as Stephen says, we're pulling phosphorus out of that system and exporting it over time. So we need to continue to replace it to keep soil fertile. So the question is with the disconnections between where we're growing food, where animals are being grown, where people are living, how can we manage the system to kind of, at least at a large scale, mimic cycling of phosphorus more like natural ecosystems, even though, farming is not necessarily a natural ecosystem itself.
How much loss of phosphorus is occurring through industrial animal operations? There's a lot of phosphorus. Well, it's going to the crops we grow for animals. The waste pits usually are just lying there. I mean, there's no really good system for dealing with manure pits and other waste products of that. What would be ideal for, we need a few animals on the farm if they're not used for meat, if they continue to be there. What would be the ideal situation vis-a-vis phosphorus and animals?
Yeah, I would actually argue there are good systems. There are not as good systems, and there are bad systems out there for managing manure. I mean, it is a challenging material to manage, in part because the number of animals on a given acreage of land is much higher than it would have been in a pastoral system long ago. So we just have a lot of manure to deal with, and not necessarily the land base to deal with it. But that manure was often spread in some way to support the growth of feed crops. So in the Northeast where I live, that's often corn silage. So it is kind of circular in the sense that the manure is going to help grow feed that will be fed to dairy cows, for example. But there's some like inherent limitations to how efficient you can do that, partly because it's the population of animals can get too large for a given land base, like I just mentioned. That means we just kind of have more manure than the soil needs to be fertile. And then the question becomes, what do we do with that excess? There's also some like devil's in the details type of stuff where the amount of nitrogen relative to the amount of phosphorus in manure is not in a ratio that meets what crops need. So if we apply manure to meet nitrogen demand, which is often done, that will inevitably cause excess phosphorus application. So, I've worked on systems where we're trying to figure out ways to extract phosphorus from livestock manure so that we kind of have it in a separate pile, literally, that we can manage in a different way. But these are kind of emerging techniques that there's still a lot to figure out about how to do it best. We have not completely solved that issue, but it is something that is an active area of research. And if you look at a map of the size of various phosphorus flows in the United States, for example, livestock manure is going to be a big one. So that's a key area for us to think about the phosphorus cycle and how we can make it more sustainable.
And let me just jump in. First of all, I'll put a plug in for a whole other episode on cows, because I think that's an important thing. We grow an enormous amount of corn in this country. None of it goes directly into the mouths of humans. It goes into cows and cars, both of which are really bad ideas. But I also want to not make a distinction right now between feedlots and cities because both of them are creating manure full of phosphorus that is not going back to the farm, right?
Mhm.
And so recycling of cow manure is a challenge, as Eric just said, and there's work being done on that, and it's going to need to be done, and we're going to need fewer animals. Like there's no answer to sustainability that doesn't include fewer cows, which is why I want a whole episode on cows if you're interested. But cities
sure.
are the food that goes into our mouths has phosphorus in it too, and that comes out the other end and it goes into sewage treatment plant or not. And so we actually don't have an answer on the cow side, except fewer cows would be better. But we also don't have an answer on the person side. And so we have a lot of thinking to do about how to manage this. There's lots of low-hanging fruit. Eric said a really important thing earlier, which is we could use less and get the same amount of crop production, and that would be a great start. And the reasons I think that farmers don't do that is the risk of underproducing is more scary than the risk of spending a little too much on phosphorus. And that's the
Mhm.
same reason they overuse nitrogen. So there's lots of modern technology that can help people make decisions, better decisions about application. But even if we do it really, really well, we still have this recycling problem. And that is a technology that we need to be investing in. The good news is that we are not running out of phosphorus in the short term. We have a lot of phosphorus left, geopolitics aside. We have a lot of phosphorus in the world. And because it's irreplaceable and necessary, we will spend what we need to spend to get it. There's phosphorus in lots of rocks, just the concentration goes down as you get away from these really rich deposits. So we have time to figure this out. But we need to figure this out because it is ultimately, as Eric quoted Isaac Asimov, like it's life's bottleneck.
Mhm.
There is a lot of phosphorus on the earth, but apparently most of it is not accessible. We take a great deal of mining to get it. Is that what the situation is?
Yeah, I think with any resource like this, there's questions of quality, right? Like there's rock that is higher quality in the sense that it's easier to obtain a useful amount of phosphorus from it. And then it kind of goes down, to moderate quality to lower quality. And, we tend to, with any resource, start with the higher quality material we have access to. And then move on down the line if we have to. And, as Stephen alluded to, necessity is the mother of invention. So with
Yeah.
something like this, I would predict that we will get extremely clever at acquiring phosphorus from a variety of materials because we'll have to eventually.
So
Well,
if I
how destructive will that be, though? I mean, most mining processes are pretty environmentally horrible.
Well, let me jump in on that because I think to Eric's point, there's a huge capacity for innovation here. So let me just give you a sense. Like if you're talking about the sort of high grade phosphorus deposits, like the best in the world, maybe you're talking 30% phosphorus for lack of a better term. And then, low grade deposits might be 10%, right? But soils actually have a huge amount of phosphorus in them everywhere, and most of it is not accessible to the crops that we grow right now, in part because the crops we grow are mostly annual crops that don't form symbioses with fungi, which are the sort of master phosphorus getters in natural systems. And there's a lot of work being done not to increase mining in the sense that you're talking about with tractors and explosives and all that, but actually to breed crops that are better at pulling phosphorus from the soil where they are. And if we could do that even a few percent better, if you think about the total amount of phosphorus in an average farm soil, our crops right now might have access on a given year to well less than 1% of that. So if you could get the plants to be better, our crops, natural plants are good at it, but if you could get our crops to be better at mining the soil where they are, like it would make things way, way better. We would need way less fertilizer. And there has been a lot of work done to show that actually in places where we've over fertilized in the past, you can actually go way back on the amount of phosphorus you add, and the plants can mine some of that bank account that you've built up. And Eric's done some really beautiful work to show how soils differ in that capacity, but the general idea is there. We've added a lot to the bank. There's still a lot in the bank, and if we can teach our crops to be better at pulling it out, we actually don't need to mine as much.
Mhm.
And we increase, say, the mycorrhizal fungi, which are pulling more of the phosphorus. Is there some way of having, fungus can save the world, people
Right.
say,
There are a lot
and
of
maybe that's true.
There are a lot of people working on that, and unfortunately, the way that we grow crops with tilling and fungicides, right, doesn't allow those networks, which are convoluted and take a long time to grow, but which have been with plants since the very first colonization of land by plants 400 million years ago. There were fungi on those roots, and the way we farm doesn't right now. The way we farm doesn't permit that. But people are working on that. Like that's a real, yeah. So Eric, I jump in. You're expert here.
Yeah. I mean, the way I think about it is a lot of our agricultural production, we're kind of trapping ecosystems in perpetual youth and kind of not letting the soil ecosystem develop fully in a way that in other ecosystems like forests, that development leads to places where phosphorus is very tightly cycled and with much less loss. But there's some practical constraints, and I think whenever we talk about inoculating soil, whether it's with fungi or some other microbial concoction, there's questions about like how effective will it really be. It's kind of this idea of probiotics for soil. It's kind of got a ton of potential, but also prone to snake oil salesmen as well. So, yeah, I'm really fascinated with that work. And I think we will make a lot of advancements there. And as Stephen said, we have some good examples already. If we look at Western Europe, they were able to really dramatically reduce fertilizer use and leverage the excess from the past to maintain productivity. So we know it's possible. We've seen it happen in certain regions, and we know we could do that even better probably with some innovation.
Well, another aspect of phosphorus is it binds with iron, and iron is in many soils. And then once it has achieved that bond, I think you can't get it back out. Is that so?
Not exactly. So it depends.
Okay.
It depends. Yeah. Iron is what we call redox sensitive, meaning depending on the availability of oxygen, it can behave differently in ways that could either hold phosphorus or let it go. So it's not necessarily bound forever. Phosphorus tends to bind more in more long-term stable fashion with calcium or with aluminum. But yeah, that's one of the ironies of phosphorus. As Stephen has mentioned, it's all around us, but its affinity for some of these other abundant elements is one of the things that keeps it out of reach from life.
And the answer to that question, Dale, is it really depends on where and what soil. So in the Midwest of the US, for example, iron binding, not really a big deal. Go to the Cerrado of Brazil, where Eric and I did a bunch of work. Yeah, it's a huge deal on some of the soils. So it just depends. And if you look at farms there, like the soybean farms there are adding twice as much phosphorus fertilizer as the soybean farms in the US because the iron is basically snatching up half of it before the plants can get it. It varies from place to place, but it's totally fair to say that phosphorus is a tricky thing to manage. But I think in terms of backing out, right, there's this enormous bank in all soils that our current crops don't really have access to. And so I just want to go back to that and say the answer to this, I think, in the long run, is going to have to involve developing crop systems that are more efficient and more capable of pulling phosphorus from the soil where they are, so that we can reduce the amount that we put in, because we're not ever going to reduce the amount that leaves in the crop if we keep eating it somewhere else. And more than 50% of the world's population lives in cities. That's going to increase over time. People are not living on the farm in general, and fewer every year are living on the farm. And so somewhere we need to both increase the efficiency of our crops, getting the phosphorus from the soil that's already there, and we need to work on the recycling of the stuff that leaves. But both of those things are doable. So I think of this as a critical component of sustainability over the next century. But I don't think of this as a meteor that's going to hit the earth tomorrow, right? Like I think we have time, and it's going to require a lot of effort and creativity. And it's incredibly important, but it's something we can make progress on.
Yeah.
Well, out in Salina, Kansas, so the Land Institute, Wes Jackson, I hope you know of his work,
Of course.
has perennial grasses. Are those perennial grasses then holding more phosphorus? It stays in the roots. Kernza
Yeah,
is in cereals now.
yeah.
It's a perennial grass that can be pruned and it continues to grow. And is it more mature, as you say? It's not a young crop. It's been there for a long time.
But just in general, I think whenever we think of alternative agricultural systems, we have to keep in mind various trade-offs that need to be navigated. Like some of these systems might kind of initially have clear environmental benefits, but with lower yields, when we kind of think about, the impact per unit food produced, it might not look as good, or it might look as good. It just depends on a lot of factors. So we when we look at various agricultural systems, we look at the nutrient cycles, nitrogen, phosphorus, but also the yields that are being produced, the fossil fuels that are needed to manage those systems. There's just a whole range of factors that I would just encourage anybody to just keep in mind that it's pretty complicated and the trade-offs can be surprising sometimes.
I'll just jump in on the perennial versus annual in case this is a terminology that maybe the viewers aren't familiar with. So many of our crops are modified grasses. So corn and wheat and rice are modified grasses, and they're planted and they grow up in a year, and then they die or we kill them and we harvest the seeds, and then we do it again next year. So that's an annual. But
Mhm.
perennials are things that live from year to year. And maybe in the case of some of our perennial crops, maybe they live 4 or 5 years or something like that, and then you replant. And that those have the advantage of building much bigger rooting systems that can access, for example, phosphorus that's deeper in the soil. They can help prevent erosion and loss of phosphorus and other nutrients to waterways. So there's a lot of upside to perennial things. One of the downsides, or there's sort of at least three downsides at the moment. One downside is just from a basic plant economy, if you're investing a bunch of your carbon that you got from photosynthesis in roots below ground, then you don't have as much carbon to grow above ground, which means potentially that you are not producing as much food because you're producing a whole bunch of roots. Another thing, just from the farm economic side of it, is we've been growing wheat, like which is a direct competitor to Kernza, for a really long time all over the world with huge amounts of industrial inputs and science behind it. So that, for example, wheat grows to a particular height that's all the farm combines are built to harvest. And Kernza, right now, because it's sort of experimental and new and people are trying it all over the place, it doesn't do that, right? It hasn't been bred to do that by the incredible technology that agriculture has deployed over the last 60 years. So it's just much harder to harvest. It's more expensive. It's all those things. And this is true of any disruptive technology. It has to be proven in a small plot, and then it has to get across the so-called valley of death, right? Where it has to compete against an established, very optimized system with very low profit margins. And it's hard to ask a farmer to start growing Kernza where it's going to take them a decade to even begin to be able to compete with wheat, right? Unless the people are willing to pay 5 times more, right? And this is true about new battery technology. It's true about any disruptive technology. And so I think Kernza is sort of facing that problem right now.
Mm.
It works at the Land Institute, works on experimental farms. Whether or not farmers are going to adopt it I think that's an open question, because all of the tech and support and government funding and Caterpillar tractors, those are all made for wheat. They're not made for Kernza, right?
Just real quick point that for all the reasons Stephen just mentioned, I'd be kind of skeptical of something like Kernza being a solution today, but I would be very enthusiastic about investments in innovation in that space, because over time it may become a better and better solution.
I think that's very well said.
Yes, indeed. Well, we need to shift so many of our systems if we are to have life continue on this planet. And certainly farming is one of the most critical aspects of our situation. So it's very interesting. And thank you both for enlightening us about phosphorus, about which most of us know almost as little as you can imagine. So thank you, and appreciate your being here on Facing Future.
Thank you, Dale. It was a lot of fun.
Yeah, thanks for having me.